Good evening, everybody. This is Nikun Shetty from Team 1. I would like to welcome you all to our project presentation. The project which we are proposing today is called TrueSight. It is an AI powered image authenticity verification system. We're excited to walk you through everything what we have built and planned so far. Let's go ahead. Before we dive in, let me quickly introduce to our team. We are a team of 5 members. Dipesh is our ML and AI engineer. Parth Desai is our project lead, handling front-end development and UI UX. Ayush is our back-end developer and lead our research effort. Manas is our full-stack developer and handles testing, where I serves as back-end developer and DevOps engineer on the team. So let's go ahead. Now let's talk about who TrueSight is built for. We have defined three key user personas. The first is Sarah Chan, a digital content moderator at a major social media platform. She reviews a large number of images daily and needs to quickly detect manipulated or duplicate content and reduce manual review time. The second is Dr. Alex Kim, a cybersecurity researcher. He studies deepfake and image forensics and relies on measurable, reproducible evidence. TrueSight gives him a detailed similarity score and confidence matrix to support his research. The third is Mark Jonas, a news media fact checker. He verifies image before they go to print, works under tight deadlines, and need a clear, truthworthy result. TrueScience gives him confidence score and a transparent verification history so he can make fast and reliable decisions. Let's go ahead. So what exactly is TrueSight? TrueSight is a hybrid image authenticity verification system. It evaluates whether an image is original, manipulated, or visually similar to previously stored content. Importantly, the system does not claim to provide or prove absolute authenticity. Instead, it provides a structured and measurable similarity analysis using both structure and semantic technique. At its core, TrueSight generates perceptual hash fingerprint, extracts neural embeddings using CLIP, compute similarity using Hamming distance and cosine similarity, and applies a hybrid scoring model to classify image. All of this is logged for reproducibility. Let's move to the next slide. To keep ourselves aligned as a team, we established a formal working agreement at the start of this project. We hold weekly meetings every Monday and Friday, with additional sessions before deadline. Everyone is expected to respond to message within 24 hours. All work must be completed at least 24 hours before submission. No last minute drops. On the technical side, all code goes to GitHub using feature branches and with a clear commit message and basic testing before any task is marked completed. Each task has a single clearly assigned owner. So that's it from my side. Now Deepesh will carry forward the presentation.
Hi, I am Dipesh Katudia and I'm here to present the presentation on MVP. So our project is TrueSight and our Sprint 1 MVP features include the upload an image into the system, then register an original image for future reference, also analyze an uploaded image using only the perceptual hashing algorithm and displaying a basic trust result. Also displaying the p-hash based identifiers and maintain history of image and verification and activity, and would also have a store image and verification data using SQLite. In our true side, the technologies we are using is the front end, back end, also programming languages. We are using Python and JavaScript. For the backend framework for creating an APIs, we are using Fast API, Uvicon for server running, also Pydantic for data validation. Also in front end, we are using React and Next.js, which will have a user interface development. Also Axios and Fetch API for the client server communication. Also in image In machine learning models, we are having a perceptual hashing, a Pillow, a OpenCV, and PyTorch for similarity computation. For generating the trust scores and the validation, we are using Hamming distance, cosine similarity, and NumPy. For algorithms, we are having the perceptual hashing, clip embedding, hybrid scoring model, cosine similarity, and Hamming distance. So in perceptual hashing is basically it will generate a visual fingerprint of an image. So let's say it will convert into the binary form in it. So in sprint one, we'll be covering only perceptual hashing. So this is our system architecture. As we can see, we are having a front end, back end, and persistent storage. So for in front end, we are having a user interface where it will be having a drag and drop of the image, which will be uploading to for the verification. It will have a trust score visualization, the result dashboards, also analysis history and real-time status. So that HTTP request will be sent to the backend layer, which will go to the fast APIs that we have been developed. So API endpoints are post registers, post analyze, get registrations, get analysis, and get export, and also the health check, the final one. And for the detection methods, we are having a clip model, a p-hash generator, and Merkle ledger. So currently we'll be using only p-hash generator, and that will go to the SQLite database, which will be having a SQL queries, and that then it will go to the persistent storage. So the data flow of the image registration will be the user will upload an image via front end. That front end will send a post request slash register with an image file. It will have a backend will receives an image, then it will generate a p hash. So in sprint one, we'll be only covering generating the p hash, and lastly, it will just give me the basic trust score. So this is the data flow of the image analysis. The user will upload an image in front end again. It will have a post. It will the backend will receive. So it will for the image analysis we'll be only having p hash, not clip embedding. Clip embedding will be executing on the next sprint. Also, it will have a query database for all registered images. It will compare the Hamming distance and compare the cosine similarity. Also, the it will have a trust score, calculated trust score that will be stored in the database, and then it will return the result in the front end. So this is our deployment architecture. We will have a Docker compo. We'll be using Docker to deploy, so it can run in any machine.
So now I will explain the product backlog for TrueSight. The product backlog represents the complete list of features and work items required to build the TrueSight system. These items are prioritized based on importance and implementation order. Our backlog includes core functionalities such as image registration, image analysis, similarity computation, classification, and backend API testing. Each backlog item is written as a user story which describes the feature from the user's perspective. This helps us ensure that development stays aligned with the real needs of users such as journalists, content moderators, and cybersecurity researchers. During sprint planning, the team selects a subset of these backlog items and move them into the sprint backlog, which represents the work committed for that sprint. Now, for sprint one, our goal was to build the first working MVP of TrueSight using perceptual hashing. The team committed to 21 story points for this sprint. The main tasks included image registration, image analysis, SQLite and SQLite storage with history tracking, Hamming distance comparison, image classification, backend API testing. The sprint goal was to create the first usable version of TrueSight where user could register an image and analyze an uploaded image and receive a basic trust result using p-hash verification. The sprint focused on establishing the core architecture and backend functionality of the system. And now moving further with the stories and tasks committed for the sprint one. In sprint one, we implemented several user stories with defined acceptance criteria to ensure that functionality worked correctly. For example, in Scrum 5 image registration, the user can upload a JPG or PNG image and register it as an original image in the system. In Scrum 6 image analysis, the user uploads an image and the system analyzes it to determine whether it is a similar to previously registered image. For Scrum 7, we implemented SQLite storage and verification history, which allows the system to store the hash value, timestamp, and verification result of each image. We also implemented Scrum 8, where images are compared using Hamming distance, allowing the system to measure structural similarity between images. Each story had a clear acceptance criteria, such as validating file types, returning similarity results, and showing warnings when invalid inputs are provided. And stories completed in sprint 1, like in sprint 1 several core stories were successfully completed. First, image registration was implemented, allowing users to upload and store images in the system. Second, SQLite storage and history tracking were completed, which enables the system to record image registration and verification activities. Third, we implemented Hamming distance comparison using phash, which allows structural similarity detection between images. We also partially implemented image classification, where the system provides a basic trust result for analyzed images. As a result, we delivered a working MVP that support image registration, phash identifiers, similarity comparison, and history tracking. Now, moving further, some planned stories were not fully completed in sprint 1 and were carried forward to the next sprint. The first is full image analysis, which will include both phash and clip based similarity. The second is completing the full classification logic with all verdict categories. The third, backend API testing, where automated tests will validate the API endpoints. These tasks are carried forward because Sprint 1 prioritized delivering a working MVP with the core functionality. In the next sprint, the team will focus on like enhancing the verification and accuracy by adding clip embedding, improving classification logic, and implementing automated testing.
So, for this part of the project, I focused on building a clear and structured testing plan to make sure every major features of the system works reliably. In total, I designed 21 test cases, all planned for the Sprint 1 validation. This test cases covers to full workflow of the application from image registration to backend API behavior, so we can verify both functionalities and user experience. So coming on to the registration module, the first group focuses on the registration flow. I created test cases to confirm that valid JPG and PNG images are accepted, invalid file types are rejected, and system handles cases where no file is selected. This ensures the platform proper input validation right from the start. Coming on to the second point, which is image analysis, I test the image analysis module. This cases check how the system responds to different type of images like likely real, unreal, or images with no matching records. I also included a test for when the user tries to analyze without selecting a file. This helps validate both the model decision logic and the UI error handling. Coming on to the third point, history. For the history selection, I created test cases to verify that the system currently display past analysis, handles an empty history state, and orders entry in reverse chronological order. This ensures user always see the most recent result first, which improves the usability. Then Hamming distance, the next set focuses on the Hamming distance calculation. I tested three scenarios: identical images, slightly modified images, and completely different images. This case help confirm that the similarity checking logic behaves consistently and provides meaningful comparison. The last second is classification. For classification, I validated all four possible outcomes like likely real, uncertain, likely AI, or manipulated, or not registered. This ensures the model output categories are mapped correctly and displayed accurately to the users. Then finally, the backend API testing. I included backend API test cases. This verify the health points, the registration endpoints with valid images, the analyze endpoint returning the correct verdict, and proper handling for invalid file type. This ensures the backend is stable, predictable, and aligned with the front-end behavior. Then overall, these 21 test cases give us full coverage of the system core features and help ensure that the applications behave reliably before moving to later sprints. Moving on to the progress we achieved in the sprint 1, here are the user stories that we completed or mostly completed during the sprint. The focus of the sprint 1 was to deliver a functional MVP centered around image registration, p-hash generation, similarity comparison, and basic classification. Overall, we made strong progress across all the core components. First, let's talk about the image registration. The first completed story is image registration. User can now upload and register an image into the system. This forms the foundation for all the downstream features like pH generation, comparison, and classification. Second, Scrum 7, which is SQLite storage plus history. Next, we will implement SQLite storage along with the history features. Every registered image and every verification result is stored and can be viewed later. This ensures persistence and gives users a clear record of past analysis. Then is Hamming distance comparison. We also completed the Hamming distance comparison story. The core p-hash based matching logic is now working, allowing the system to compare the structural similarities between the images. This is the key part of determining whether an image is identical, slightly modified, or completely different. Then as the image classification, we made partial progress on the image classification story. In the current prototype, the system can display basic trust law result or tags such as likely real, uncertain, likely AI manipulated, or likely AI, or it's likely an manipulated image. More advanced classification logic will be refined in the future sprints. Overall, sprint 1 delivered a working MVP that includes image registration, p-hash generation, Hamming distance comparison, SQLite storage, and basic classification. This aligns perfectly with our sprint 1 plan and gives us a strong foundation to build more advanced features in the next sprint. Now I will walk you through the stories that were not fully completed in sprint 1 and will be carried forward in the next sprint. These items mainly involved advanced analysis and automated testings, which were initially deprioritized so we could deliver a usable MVP first. So the first is full image analysis. The first incomplete story is full image analysis, while p-hash based comparison is working, the combined analyze using both p-hash and clip similarity is not yet finished. Clip integration requires additional model processing and tuning, so this will complete into the next sprint. Remaining work in Scrum 9 is image classification. We also have remaining work under the image classification story. Although the prototype shows basic trust tags, the full 4 verdict classified logic still refined. This includes image threshold, confidence scoring, and final decision mapping. Last, uh, last second is the API testing, the backend API testing. Another story carry forward is backend API testing, the automated test suite for endpoints like registration, analysis, and error handling is still pending. Completing this will help ensure reliability and prevent regression in future sprints. So the main carryover task includes adding clip based analysis, expanding the trust scoring logic, completing the final classification behavior, and implementing the backend API test suites. These items build on the MVP foundation will significantly improve accuracy and stability. So here's the reason for the carryover. The reason for these stories were not completed in the Spirit 1 prioritizing delivery. The first usable MVP focuses on registration, p-hash generation, identifier, and history. Advanced analysis and automated task testing will were planned but not essentially for the initial working version, so they naturally move into the next sprint. So now I want to highlight the key metrics of the sprint 1. These metrics help us to understand how we planned, how efficiently we executed, and how closely we stay aligned with our sprint goals. First you see is the burn down chart. Starting with the burn down chart, this shows our progress across the sprint. We began with 21 story points, and you can see a steady decline all the way to 0 by the end of the sprint. The actual progress line stays close to the ideal line, which indicate that our pacing was consistent and we didn't experience major blockers or unexpected delays. Next, coming to the team velocity chart. Here, the number of planned story points and the number of completed story points are the same. This means we delivered exactly what we committed for the sprint 1. It is a strong indicator of accurate planning and reliable execution. Completed versus the committed ratio. Finally, the completed versus the committed ratio is 1, that's calculated as 21 completed test cases and 21 committed. As a ratio of 1 shows that the team met all the planned deliverables for the sprint, which is ideal for an MVP focused iteration. Overall, this metric shows that sprint 1 was well planned and well executed. We maintained steady progress, delivered everything we committed to, and established a strong foundation for the more advanced features coming in the next sprint. So to wrap up the sprint 1, we concluded a retrospective to reflect on what went well, what could be improved, and what actions items we want to carry into the next sprint. This helps us understand our strength as a team and identify areas where we can work more efficiently. So what went well? First, several things went well, and that were really well. So we successfully set up the core project structure for both the front end and the back end. We also delivered a working MVP that include image registration and p-hash based verification. The main flow, uploading, registering, analyzing, and viewing history, was fully implemented. Everyone contributed across development, documentation, and presentation preparation. And finally, we incorporated feedback for the professor, especially improving the persona slide. What can be improved? There were also areas where we can improve. Some of the planned sprint 1 feature turned out to be more ambitious than what we could realistically finish. We also spent extra time setting up dependencies and environment which slow down deployment, which slow downs the development, and coordination can be stronger, especially when it comes to finishing testing and advanced analysis of earlier in the sprint. And a few slides and technical explanation needed refinement after feedback. Action items for improvement. Based on this observation, we identified several action items. We want to break large stories into a smaller, more manageable task. We will finalize environment and dependencies earliest in the sprint to avoid delays. We improve internal check-ins so progress is tracked more consistently. We will complete carryover task at the very beginning of the next sprint, and we will review presentation slides as a team before the final submission to ensure clarity and consistency. Overall, the retrospective helped us recognize that while sprint 1 was productive and successful, there are clear opportunities to streamline our workflow and deliver even more efficient in Sprint 2.
So now I'm going to talk about the stories planned and committed for Sprint 2. So in Sprint 2, our main focus is to improve the current system and add more powerful verification features. Some work is carried over from Sprint 1, such as completing the full image analysis workflow, improving the classification logic for verification result, and completing backend API testing. For the new Sprint 2 task, we plan to add clip based image similarity matching, which will improve how our system compares images. We will also expand the result details so user can better understand how the trust score is generated. Another improvement is enhancing the trust score logic by using multiple verification factor instead of relying on a single method. We will also strengthen the history and audit trails system so user can track previous image verification. Additionally, we will improve the user interface for displaying analysis result and perform end-to-end testing to ensure the entire system works smoothly. The overall goal of Sprint 2 is to enhance trust TrueSight beyond the basic MVP by improving matching capability, verification logic, and system reliability. Then let's go to the next slide, which is project demo for Sprint 1. This slide shows the current working MVP of our project from Sprint 1. At this stage, the application supports the basic image verification workflow using perceptual hashing. The system allows user to upload an image either register it in the system or analyze it for verification. When an image is analyzed, the system generates a trust result along with the verification tags and p-hash identifier. The system also keeps tracks of image registration and analysis history. All this information is stored using SQLite database, which support the basic backend functionality of our MVP. Then here is our application screenshot for Sprint 1 MVP. So this slide shows a screenshot of our current MVP application interface. The interface allows user to upload an image and perform verification through the system. It demonstrates the basic workflow where the user uploads an image, the system processes it, and then returns a trust result based on the p-hash comparison. The screenshot represent the working prototype or developed through during Sprint 1. Then next is a backend API for Sprint 1. This slide explains the backend API developed during Sprint 1. This API supports the main workflow of TrueSight system, including image registration, verification, and history tracking. The get health endpoint check whether the backend server is running correctly. The post register API allows user to upload an image or upload and register an image, and the system stores in SHA 256 hash and p hash in the SQLite database. The post analysis API or analyzes an upload image and compares its p-hash and stored images to generate a trust result and verification tags. The history API is written records of previously registered image and previous image analysis. Overall, the backend handles image uploads, generate p-hash identifier, and stores data in the database, perform verification, and returns the result to the front end. Next is a group wiki page link. So this slide contains the link of a project wiki, and the GitHub repository. The wiki includes all the documentation related to a project, such as project description, technology stack, sprint deliverables, architecture design, burndown chart, and team working agreement. It serves as a central place where all project updates and documentation are maintained. So that's it from our side. Thank you for listening our presentation.